This meeting is being recorded.
Hello, can you all hear me? Perfect.
Is our quiz today on the rest of module 3, or is that on module 4, like the videos that we just watched?
No, it's on the rest of module 3. But I'm still going to have to say this again because we're kind of early. I just realized midterm is next week. So your midterm is this time next week, scheduled on the syllabus. It's 10/6, October 6th. That means you have only one more class.
That's kind of scary.
It's just going to be like these quizzes. Only thing I'm considering is to put maybe one question in calculation. And I'm still not sure if I want to go that route. Because if I go that route, it's going to be to have you guys put the final answer so Mojo can auto grade, then upload your solution. That's how I can give partial credit. Because it's easy to follow all the steps and make one small calculation mistake. And if you depend on module quiz, yeah, you get 0, even if the steps are all right. So that was the only part I'm still thinking. But easy to see that many of the questions will be similar to what you've been doing. And I might actually just stop wherever we get to today. That way, I don't add new material. Okay, now that Isaiah is here, I'll still have 1 minute. Just gonna wait before repeating it again. Still able to write here, right? Yes. I don't know if I like the back. But the harder part is how to control the color. I'm gonna pretend like I want to record. Then see if I can change the color here. And if I leave the recording mode, it keeps, no, reverse back to black. It's all good. Okay, so what I was saying earlier is that quiz 6, which is the one you'll do today, will cover the rest of module 3. And per the syllabus, your midterm is next week. It's October 6th. So the plan is to stop at module 4G, which is where going to stop today. So it's right here. I wouldn't even get here. Yeah, I think I'm just going to stop right here. I already recorded videos through this point, 22. So I'll stop right here instead of trying to cover all of module 4. So you're not learning something new on Thursday. You're learning something new on Thursday, but it's not going to be tested on Tuesday next week. Good. Any questions about that before moving into what we have today? Any questions on modules 1 through 3 before we move on to 4? Any questions on any of the quizzes? So if you have any questions on any of the quiz questions, I mean, you can always ask right after the quiz. Okay, so I started this in the last class, and I know I covered this and this. And I covered out the rest of that in the videos. So have you all guys watched the videos? Good. So any question on this? What's this value called?
That's your UCS. So the yield stress, is that necessarily when you don't have confining stress or yield strength? Or is that where it differs from the straight line?
Yes. The latter is the correct statement. And in any of this, wherever it differs, so this will be the yield stress at this confining pressure. This will be the yield stress at this confining pressure. This will be the yield stress at 0 confining pressure. So yield stress is not tied to the confining pressure, just like the rock strength, right? The compressive strength of the rock. So what's this value? This is UCS, which is rock strength or rock compressive strength of the rock at 0 psi, right? That's why it's called UCS, unconfined. This is still compressive strength, but at this value. This is compressive strength at a confining pressure of 5,000 psi. So that's a similar way we describe the yield stress. Yield stress at 5,000, yield stress at 1,000, yield stress at 0. Any other questions on this?
For yield stress, does it always increase when you increase the confining pressure, or does it kind of looks relatively constant for all three? I'm not sure if I'm just looking at it wrong, but is it always increasing as you increase the confining pressure?
It looks like it does, yes, based on the laboratory data, yes. What is not really, you will see we never really talk about yield stress in the rest of the presentation. What we care more about is the failure point, the point at which the rock fails, because that's the point we switch to plasticity. So there's going to be a lot of conversation about the failure criterion. And after that, you just switch to a plastic model. But yeah, to me, it looks like it gets higher with higher confining stresses. And this is just purely experimental data. Any other questions on this? Mohr circle. Why do we use the Mohr circle? What does it give us?
Doesn't it give, like, whenever you rotate an object that has stresses acting normal to it, it gives the equivalent strain based on that rotation.
So you're talking about it giving you this too? Yes, but in terms of a bigger picture, which is going to be clearer when you look at multiple more circle.
It would give you at what point the rock will fail. At what point the fracture, it will fracture.
Yes, it will give you at what point the rock will fail at any confining pressure. That's the main advantage. Because, yeah, you may be applying a certain stress in the lab that may not be equivalent to the stress state in the subsurface. And even in the subsurface, when you start to produce and you begin to drop the pore pressure, well, the effective stress begins to decrease. The rock strength will change again, right? Because it's always a function of the confining stress. And you need to know the rock strength at that new value. So the Morse circle gives you a way to predict the maximum, this maximum value, which is the maximum strength of the rock at any confining pressure. Because it's a circle, right? You start with this confining pressure S3, well, then you draw the circle. Now you know the maximum stress that the rock can hold. It can't hold anything more than that, it's going to fail. So it defines the maximum allowable stress state. Maximum allowable stress is this value right here. And it's this maximum circle you can draw under the failure envelope. So it's a graphical procedure originally. Then we came up with mathematical expressions that we can use to predict the shear stress on the surface after failure, the normal stress on the surface after failure. So I will go back to the previous slide. So is it very clear what beta is? Because it's very important to know what beta is. Angles can be measured in any different way. So what's beta? How do you define beta?
It's the difference. It's the angle from your principal stress at which the material is going to fracture. So from your fracture to your normal stress.
Where on the fracture?
Normal, perpendicular to the fracture.
Correct. Is the angle between the fracture normal and the direction of the maximum principal stress? In the context of triaxial test, that direction of S1 is vertical. So it's basically, and actually in the subsurface, S1 is typically the vertical direction. But that assumes you're looking at a normal faulting regime, right? So it's the angle between the vertical and the normal to the fracture surface. That's the one I'm trying to emphasize, because it's not the angle between the vertical and the fracture surface. No, it's the angle between the vertical and the normal to the fracture surface. And so even if your fracture surface is like this, the angle is always going to be between 0 and 90, right? If this is your fracture surface, the normal is here. It's an angle between the vertical. There's no direction component to it. It's just the angle between them. So this will be better. Question? I thought you had a question. No question?
No, I'm just kind of thinking about it.
Okay.
Yes, I did have a question on. So you said that your normal stress is an effective stress.
Correct.
And I know you went over it, but I just want to be clear. Is your sigma 1 and sigma 3, are those effective or total?
They are all effective.
Okay.
So this axis, any stress you put on it is effective stress. On the x-axis, it's the y-axis that is the shear stress. And in the context of the textbook, which is what we're following, anytime you see sigma, it's It's effective stress. The only point where I had mixed it up was when we talked about Hooke's law, and I still use sigma. But it's very easy to know when it's effective and when it's not, right? Whenever you can have fluid in the problem, yes, and you see sigma, it's effective stress. But I still like to use sigma prime, which is the standard nomenclature, even though the textbook chose to use sigma for effective stress, S for total stress. So sometimes you see me use this for effective stress, but I try to use this as total stress all the time. So for the rest of all the course, yes, S will be total stress, sigma will be effective stress. The only point where there could be a little bit of confusion is in Hooke's law, when I used sigma as a Cauchy stress tensor, because that's how we work in the standard material deformation. And it's easy to see because I talk about it in the sense of material without a pore spaces first. So any stress you see there, you know it's total stress. Then we now move over to effective stress, and then I begin to use sigma prime. Good. So yeah, this is all effective stress. And how about this? Can you have effective shear stress? No, because on the off diagonals you have 0, right? For pressure. So if you take away 0 from your total stress here, you still have tau. It never changes. And that's what I explained extensively in that video. Any other questions on this? So what does this mean? The circle term.
That's your radius of the circle.
Correct. And since we are looking for tau, right? So you're here, right? And then we want to get tau. So you just multiply by sine of 2 beta. And that's how it reduces it to this. This is the same thing, right? Whereas this gives you this coordinate. And you just need to move it by this value. So this value is always negative. I explained all of that. Any other questions on this?
How is that value always negative?
You already know the range for beta, which is what I was trying to get to previously. Beta, if your if your fracture is completely horizontal, then this is the unit normal, right? I mean, the direction of the fracture normal, and that beta will be 0, right? That's the least value it can be. What's when it's vertical, unit normal, I mean, fracture normal, which is same as direction of the unit normal to that surface. It's 90 degrees away from the vertical. So beta goes from 0 to 90. So cos of 0 to 90 is cos of 0 through 180. So it may not always be negative, actually. You're right, yeah. It can be positive, it can be negative. How do we know? Well, if you draw the plot of, oh, you can't draw below this stuff. Cosine goes from 0 to, from 1 to -1. So that value can go from 1 to -1. It just so happens that, okay, so how do you know the direction? I think it's purely a geometrical stuff, right? So this is your normal. If it's greater than 90, then this line goes backwards. Okay, I see. So 90, above 90, that's when it's negative. Do you see that? Below 90, yeah, this line will be moving forward and you will have to add. And that makes sense from from this stuff, right? This is 0 degrees, this is 180, this is 90. So it's positive between 0 and 90. Then it goes negative between 90 and, hold on, this is 360, right? So this is 180.
That's a full cycle. It goes 1 at 180 degrees. It's -1.
Yeah, which is what you see here. So this is the interval when it's negative, between 90 and 180, which makes sense. That's when the angle points backwards on this half part of the, I don't know, I think now it's looking too crowded, right? So from 0 to 90, if beta goes from 0 to 90, not beta, 2 beta, right? Exactly. 2 beta is what we are looking at here, right? Beta is 0 to 90. 2 beta is 0 to 180. So as long as beta is 0 to 45, that stuff is going to be positive. So you will, this stuff we're putting to the left here, yeah, it's because this angle was greater than 90. If that angle was here, less than 90, then your sigma n will be to the right-hand side. So you see, that's why it has to be positive. You'll be adding this on top of the original location. Exactly. I can explain it again if it's not very clear. So 90 will be completely vertical, right? And this will evaluate to 0. And you will just have this as sigma n. It's again crowded. Let me explain it one last time, where everything is all cleaned up. This is very clear to see what that takes you to, right? That takes you to this point. What you're looking for is sigma n for any beta. Okay. If beta is 45 degrees, then 2 beta is what? 90 degrees. And cos of 90 will be 0. So if 2 beta is 90 degrees, yeah, this angle is not going to get this far, right? 90 degrees will be right here. And this will be 0. So that is sigma n, which makes sense. If it's greater than 90, which is this example, I mean greater than 45 degrees, which is the example you have here, then the angle will go past 90, right? Which is why it's to the left-hand side of the circle. And now it's negative. And you already see here, right? This is 90. When you go past 90 is when the cosine becomes negative. So that's why that is negative. So it's not always negative. If your angle is between 0 and 45, say 45 degrees in particular, you'll be here. Right? So sigma n is not to the left of this radius, it's to the right. So this is your sigma n. So how do you get the correct value? The first component took you to this point, right? Well, you now have to add this value. So this will be positive in that case. So the equation takes care of all angles going from, all beta values going from 0 to 90. And we're ready. Go ahead.
Didn't you say that faulting always happens 60 degrees from the normal, or would that, or from 60 degrees from the vertical in like the normal faulting situation, like this kind of thing would be where your vertical stress is the greatest stress, is your S1, or just would that not apply to these like small scale cores?
That would apply for an intact rock where you're trying to create, when you're applying the stress on it, an intact rock, no pre-existing faults. But if you have pre-existing faults already at an angle, those pre-existing faults were created when there was a different stress regime, right? Which wasn't normal. So yes, if you're trying to create a new fracture in a normal faulting regime, like in a core, it will be in the angle of 60 degrees. But why do we have fractures at other angles? Yeah, because the prevailing stress state was not normal as at that point. And again, if you have this rock, and this rock has pre-existing cracks in a certain direction, then it will fracture along that direction instead, right? Because you have pre-existing cracks. So that's one thing you will see as we go further in this topic. There is frictional sliding for an intact rock, which is no fracture, no pre-existing crack in the rock. You want to create a fracture, yeah, it's going to always fracture at 60 degrees at this normal faulting regime we have artificially created in the lab. Then there are rocks that already have pre-existing flaws in them, and those pre-existing flaws weaken the strength of the rock, and those behave differently.
Isn't that the reason we don't use the uniaxial test, because there are pre-existing cracks, but the compressive stress has kind of closed them? And that was kind of fuzzy explanation in module 3 that I didn't get too clearly, but I was.
Yes, but those were more on micro cracks. Those were more on very small cracks where it's going to be reversible, right? If you have major cracks, then it's not going to be reversible no matter what you do. You can't just close it. So those are limited to micro cracks. But yeah, you won't always have 60 degrees in all rocks you get, because again, the faulting regime you see today may not be the faulting regime when that crack was created. That's the main reason why you see angles other than 60 degrees. I think that's the main message there. But if you have an intact rock, yes, and you create normal faulting regimes, it will be 60 degrees. Good question. Any other question on this? Okay, I already came in here, and you get the idea. If you keep performing experiments at certain confining stress, the confining stress is always the smaller. There are 2 points to every diameter, right? The smaller point is always the confining stress. So you can draw the circle after performing the test. This is the confining stress or confining pressure. The other side of the circle is the maximum stress the rock can bear, which is the rock strength, compressive rock strength. My computer just went blank. So that's 4G. Then you go to a higher confining pressure, you get another diameter. That's the new rock strength at that confining pressure. At this confining pressure, then you draw another circle based on the value you get from the rock strength at this value. And as you keep drawing the circles, you can connect the tangents through all of those circles, and what you get is called what?
More Coulomb line.
The failure envelope. That's the failure envelope that goes through these different circles. And then you can approximate that envelope, which is an envelope, is a curve. You can approximate it with the Moore Coulomb failure line. So it's an approximate value. And you can see if you drill this line here, then you'll be allowing greater stress states. So you can overestimate sigma 1, which is your compressive rock strength. And you can argue, yeah, that's not accurate. We need a way to be able to precisely capture this curve. And I'd explained, well, if you use modified Occam-Brown criteria, failure criteria, then it can capture that, but where does it get the parameters of that curve? It's totally empirical. And you don't have as many core samples and all of the formation from the top to the formation of interest. And so it's not really a wise idea. So instead of all of those, we just use correlations based on well logs. So we still tend to use this linear stuff when we have core samples, but we rely on UCS estimated from well logs for formations above the formation of interest where you have no core whatsoever. But this is called what? The intercept is called what? This is tau against S1, or tau against effective normal stress. What's the intercept of that plot called?
That's the cohesive or cohesion strength.
Cohesive strength or cohesion. And what is cohesion? What's the definition of that? It's the degree to which what? To which the rock grains are held together. So for stronger and stiffer rocks, they will have a higher cohesion. So it's very important to know that the intercept you get from tau versus effective normal stress is cohesion. It's not UCS. So you will have to draw the smallest circle you can draw that will touch the origin and touch the line. Actually, there's only one circle you can draw under that line that will touch both this origin and the line. Then where that circle touches the right side of the circle, where it touches the effective normal stress, is your UCS. So you get this equation for this line first, which is defined by the intercept and the slope, right? The slope of the line is called this. I already explained all of those, right? And that's how you get UCS. So UCS is not S naught. You can get UCS, which is CO, from S naught, like shown here. And the equation of this is basically the equation of a straight line, right? Y equals, this is C or B, which is your intercept, and this is your slope, and this is your Y, your X. And again, this is for intact rock. If an intact rock wants to fail, yeah, it's going to fail along the 60-degree line. This is the equation that governs it. If the rock had a pre-existing fracture in it, what's the equation for its failure? That's much later. So I just want to discuss both of them in this context, just because they're related. Who remembers that? I'm going to delete this. I should be able to hit delete. No.
You said if it already has a pre-existing fracture,
Yes.
wouldn't that just be what we just went over in the previous slide?
No, that fracture you saw in the previous slide was created because we applied stresses to it. It wasn't pre-existing. So difficult to clean. Anyways, I'll use this. All I'm getting to is this expression. So if you go a couple slides further down, oh, that's a frictional sliding. Oh yeah, I haven't covered this. I haven't even recorded this in the video. So yeah, we'll talk about it then. But look at this equation right here. Tau over n equals mu. This is for frictional sliding. You already have a pre-existing fracture. How will the fault blocks slip? What's the criteria at which point the fractures begin to slide? So instead of going too deep into that, I'll give you bigger perspective so you can see the big picture right now while we're here. You notice we are talking about rock strength, right? And all we've talked about is the compressive strength of the rock. The strength of the rock under compression, the compressive strength of the rock. There is also tensile strength of the rock, right? The strength of the rock in tension is the tensile strength of the rock, different from compressive rock strength. There is a third type of strength, which is the frictional strength of the rock, which will be the resistance of the fault to fault block slipping across its surface. That's the one I just showed, which we'll get to later. So we're talking about the sliding of the fault blocks across the fracture, but we assume that the fracture surface was already there in the rock. And where I was getting at is the equation is very similar to this. The equation is the ratio, the rock will slide or will slip whenever the ratio of the shear stress parallel to the surface to the normal, effective normal stress is equal to, whenever that becomes equal to mu, and that mu is different from this mu. This is coefficient of internal friction for an intact rock. So the rock is intact, no pre-existing fracture. And this one is the frictional coefficient of sliding. So it's mu without an I. That's why I wanted to make it clear right now before we get there. So in general, this will be less than or equal to this, right? At the time it becomes equal to this, then it slips. And we'll talk more about that. But the point is, this equation is actually very similar to this. So you can multiply both sides by this, right? So it becomes tau is really less than or equal to, but the point at the point at which it slips is equal to, right? So tau equals this. Let's put the slope before the variable. The slope, the variable. You see how similar it is to this, right? The only difference is cohesion. So that's the difference. Because there is no cohesion across the surface through which it slips. At the point it slips. So important to see that in context. And now you know there are three strengths of the rock, right? The compressive rock strength, the tensile rock strength, the frictional strength of the rock.
The frictional strength, that's like basic physics, right? And
Yes.
it will like there's nothing crazy there, is it?
No, that's what we're going to talk about when we get there. But basically, just this equation is all we're caring about. This is the frictional coefficient of sliding on that surface. And all you need is the shear stress on that surface, the normal stress on that surface, effective normal stress on that surface. And our focus will be, okay, we already know the definition of effective stress. As we begin to increase pore pressure or decrease pore pressure, what happens to the rock? Does it begin to slide? And that's actually what we have. That is called induced seismicity. We are injecting fluid into the rock, and all of a sudden we start to see earthquakes because we have decreased effective stress up to the point where you are now equal to this value, and you create sliding. That's the moral of the story when we get there. Good. Any other questions on the Moore cycle? So instead of working in this space where we're plotting tau against sigma n, well, what we do in practice is to do S1 against S3. Very important to realize they are different. And now, because you're doing S1 against S3, the intercept is UCS. Intercept of S1 against S3 is not S0 like you have here. It is UCS. So it's just a change of axis. S1 is the maximum principal stress, and S3 is the confining stress. And you already know when you were drawing these diagrams, right? The higher point was the UCS. Yeah, the higher point is the S1, and now that's the intercept here. And you understand that this is a different slope, right? The equation for this line is different from the equation for this line because the variables are different. So the slope of this line is referred to as N or Q. You see them used interchangeably, and that slope is not mu I. You can get mu I from it, like so. And this is the equation for that straight line: a different intercept, a different slope. And when you walk in that space of S1 versus S3, these are the Mohr-Coulomb equations. Just a different way to look at the same thing. Any questions on that? Yeah, this was well covered, nothing special, just showing data and making conclusions based on the data. Hook and Brown, you can describe a curve like this, but it uses two parameters, which you're going to get experimentally, meaning you have to do triaxial test on core samples. You will not have core samples from the surface to the formation of interest, so not really useful to go through all these complex failure criteria because you don't have rocks to get all the data you want. So we will use well logs. And what's the advantage of this? I mentioned that in the video. Nobody remembers? Why are these in purple and this is in gold? The purple are the stresses in the earth, right? Sigma 1, 2, 3, principal stresses. This is what you can measure in the lab. So that's why it's useful. You can relate stress conditions, including intermediate stress conditions in the earth, to these values which you measure in the lab. And you already know, as long as you can do a polyaxial test and you're still doing triaxial test, you really have no measurement for S2. You're assuming S2 equals S3. So that's the advantage of the modified Lade. This one, Book and Brown, advantage is you can get the curve, so you don't overestimate the rock strength at different confining stresses. But the weakness of both of them and any other failure criteria is we don't have cost on all the formations we want. This is several different failure criteria in 2D, meaning along this phase. I explained all of that before. And I said the different geometries, right, for the different failure envelopes. And the differences in shape is not as important as the difference in size, right? The size dictates the maximum allowable stress state, which is this rock strength. But the shape, yeah, it could be different, but the size is the more important. Any questions on that? And this is the reason why it's 60 degrees, which we were talking about before, right? Intact rock, you create a fracture, yeah, it tends to be along the 60-degree line. And because for this case, whenever you now have, if you had no fracture, you will get it in 60 degrees. When you create the fractures, the strength of the rock is now different. It's much weaker. And that's why for the intact rock is this. For the weak rock, that's what the substrate is all about. Then the line is lower, meaning the intercept is lower. And because the intercept is lower, the circle you can draw under it is smaller. And that severely restricts the strength of the rock. So now it's much smaller. And the question Donald's theory tries to find is, what if you can create fractures in any different angles, or if you have rocks with pre-existing fractures at different angles, which of the angles will give the least rock strength? So if I can create, I already have rocks. I have rocks with these kinds of fractures. Some, in all of them, the angle is 1 degree. In all of them, the angle is 2 degrees. In all of them, the angle is 3 degrees. And I go all the way to 90. Which of the different angles we have will give the least rock strength? That's the question they try to address. And the theory shows it's 60. And they went ahead and did tests on an experimental or a research oil well, the KTB well in Germany. And those are those points there. It also tends to indicate it to be around 60 degrees. And this is the equation for the rock strength, the maximum allowable strength. And when you minimize that, meaning you set beta to 60, you get this. And it not only applies for fractures at specific angles, it also applies for weak shales, weak bedding planes of shale at specific angles. And we talked about that being important for drilling, right? So if you have weak shales and the bedding plane is inclined and you're trying to drill through it, well, you need to approach it at the angle where the rock will be the strongest. Otherwise, you just lose your well. And it happens a lot. You're trying to drill to a certain well and you end up drilling making like 3 different attempts until you're able to drill through that shale. But if you can predict the best orientation of the well to give you the maximum strength, then it's not as weak as in another orientation. So the angle through which you drill through these weak bending planes is important, basically. And you can use Donald's theory to predict what angle to drill through them. Any questions on that? Since we've gone so far, let's take the quiz, then come back and finish up. Okay. Have I logged in here yet? Yes, I have. I'm just gonna do it on the other computer. Quiz 6. Show. Okay, quiz 6 is available. Can go ahead and start. Are you all done? Okay. I think we got 2 minutes.
I'm done now.
Okay. So any questions on the quiz?
I believe that there might have been a typo. It says viscoelasticity and viscoelasticity are identical, and obviously they're the same exact word.
Okay. I meant to say viscoplasticity. Okay. I'll fix that one.
I couldn't give up an easy point like that. I kind of figured that's what you were saying, but it was
Okay.
fast and easy.
And I probably graded that wrong, right? I said they are not the same. Yeah, because I meant viscoplasticity. Okay. So I'll fix that and upgrade this course.
I was thinking that was the one I'd get right.
Fix that. Okay. Other than that, everything else was fine. Good. Any questions on this? Just data.
I thought for the governing equation for flow, I thought that came from the continuity equation, and that is what created the Darcy equation.
No, the Darcy equation is different. Henry Darcy did an experiment on a pile of sand and came up with Darcy equation. Then you can walk through the derivation of the continuity equation and you get the continuity equation. Then you can substitute the Darcy equation, the V, into the continuity equation. So the continuity equation is del dot rho V equals d dt of product of porosity and density. So that V, you now put in Darcy equation, and now you have the mass balance equation, which governs flow in non-deformable porous media. So you've now accounted for the change in volume due to mechanical deformation, which will be flow in a deformable porous medium. Any other questions on that?
I had one question on another problem. It said in the Eulerian description, the movement of the fluids is relative to that of a material point in the domain. And I got it wrong because it was true for Lagrangian. So when you say material point in the domain, I thought like Eulerian was like, oh, this is the control volume, and we track the flow through it. And I guess I'm misunderstanding the definition of like the material point in the domain.
So material point in the domain will be some region in the material that you have marked as, say, this is region A. so that when the material deforms, you still have the general idea of that position of the material in the object. So region A is still this material. So you are following that material point as it deforms and all. That's the Lagrangian. And this whole thing can actually move, right? Maybe it was here before. Let's say air is moving, right? The air molecule was here before. That's a material point. But now it's here. You continue to do the calculation on that material. You follow it as it evolves through the domain. That's the Lagrangian description. Whereas the Eulerian would be, say I have a thermometer here and air is moving all over the place, and we still can continue to make measurement at that particular instance in space. X, Y, Z never changes, but time is changing. But in the Lagrangian, X, Y, Z is getting updated. And how do we keep track of that changing X, Y, Z in the Lagrangian? The displacement. Remember, it's displacement we solve for in geomechanics. So what's displacement? Well, it's that vector where it is now relative to where it used to be. So this minus that, that's the displacement. And so when you solve for displacement, you are now able to figure out the new material location. Okay, so back to rock strength. This is obviously compressive rock strength from well logs. And we are using UCS because we know the actual compressive rock strength can vary, right, depending on the confining pressure. So we will use rock strength, then we will use a failure line to predict the rock strength at different confining pressures, right, which is the whole idea of the Moore column. So UCS is good enough for our definition of compressive rock strength. Then, of course, we'll need μi, coefficient of internal friction, to complete the description of that Moore column failure line. So here you're looking at sandstone, shale, limestone, and dolomite, UCS on all the y-axis. And you're looking at how UCS changes with delta T, with Poisson ratio, and porosity. And as you can see, decreases with that, increases with this, decreases with that for all rock types. And I had explained all of that in the video. Any question on this? So many correlations in the tables in the book, and that's the subject of homework 3. It's just go plug in the values in the correlation and you're done. And it's for well logs. Here, what do I show? The values are different, right? This is close to 1,000. This is between 1,000 and 2,000. This is closer to 2,000. And you're predicting for the same well log, same property, UCS. But it's different because the different equations were developed using different rock samples. So it's important to choose the right correlation equations that apply to the formation you're working on. That's the moral of the story there. And this is for coefficient of internal friction for an intact rock. Anytime you have that sub I. And this is pretty straightforward. How UCS varies against clay, as clay content increases, how Young modulus varies as clay content increases. Any questions on those 2 slides? Cover these 2. And when I got here, I spent some time talking about relating this to plasticity. That, yeah, when you have plastic behavior, first off, you're going to have elastic behavior until you get to a point where the rock fails. Then you can switch to strain hardening or strain softening. So how do you know that point where the rock fails? That's what you try to get with your failure line. Then after the rock fails, if you're looking at strain hardening, the material is getting harder, right? Well, that's what we try to do here with different end caps. And as you can see, the porosity is decreasing as you cross the end caps. So trying to give you a general idea that you're going to have like 3 different material behavior. You first of all do elasticity, then you do failure criteria, then you do strain hardening criteria, which is hardening rule. So hardening rule, failure rule, you tend to see that in photoelasticity. So this would be some failure rule or criteria. This would be hardening rule. Then you have the elastic part. Different equations for those different parts of the problem. This is hydrostatic. Why? Because this is hydrostatic component of your stress. This is the deviatory part. And that's your triaxial compression, triaxial extension. Any questions on this? And that's your Camp-Clay model, originally from Cambridge and developed for clays. And now we move from compressive rock strength to tensile rock strength. And I mentioned very clearly that tensile rock strength is much lower than compressive rock strength. It's easier for material to fail in tension than for the same material to fail in compression. And they differ by about an order of magnitude. This is hundreds of megapascal. This is tens of megapascal. That's the moral of the story here. And now I don't think anyone has watched this because I just uploaded this one. All right. Okay, so maybe I can talk a little bit more on that. But that's the general idea on this slide. And on the next slide, I'm going to talk about hydraulic fracturing, which is on tensile failure, because it's like you're pulling the rock apart to create your fracture. So that force is tensile. It's tensile on the fracture surface, it's tensile on the fracture tips, and stresses concentrate on the fracture tips. I mentioned here that flaws, like those cracks, pre-existing cracks, they tend to influence the tensile strength at a much higher degree than they do influence the compressive strength of the rock. And actually, when you have planes of weaknesses in your rock, tensile strength becomes negligible, practically zero. And these are your fracture failure modes. So fractures fail in any of these 3 modes or a combination of 2 or more of these. Mode 1 is the hydraulic fracture kind of mode where you're pulling in this direction, which is why it's tensile away. You're opening up the rock. Keep in mind the stresses in the rock originally were compressive. So you are now introducing fluids in here, high pressures to tend to open it up. So it's tensile, right? So you're opening up against the fracture surface, right? So the direction of the force is 90 degrees or perpendicular to the direction of the fracture surface, which is here. That's mode 1, which is the opening mode. Yeah, opening up the fracture. You can also tend to slide the fault block across the surface, which is mode 2, which is the kind of stuff you get in faulting, right? You have displacement along the surface. And I believe everybody already now knows the difference between a fault and a fracture. It's not size, it's that there is displacement along the fault surface when you have faults. So there's movement. If there's no throw, no movement, it's a fracture. If there's movement, it's a fault. So that movement along the fracture surface is the sliding mode, and that's mode 2. The shear stress is shear because it's parallel. Here it's normal, right? Here it's parallel. So it's a shear stress and it's normal. No, parallel to the plane of the crack, right? This is the plane of the crack. And that's the same direction as the shearing stress. So it's parallel to the plane of the crack. How about the crack front? So you might think this is the direction of the crack front, but no, the crack front is that line that starts from here and ends somewhere on the other side of the surface. is that straight line. So this is the line, this line right here, where it is at this point, right, that's the crack front, is that horizontal line. So when it opens, that line is moving in further and further, right? That's the crack front. And so that's the direction of the crack front, and you can see you're normal to it. The stress you're applying is normal to that. So parallel to the face of the crack, perpendicular to the crack front. Here is parallel both to the plane and to the crack front, and that's shear or tearing mode. So it's getting torn in this direction. It's parallel to the fracture surface, also parallel to the crack front. So those are the three modes of fracture propagation. And we focus on the one that borders on hydraulic fracturing, which is which mode? Hydraulic fracturing is which mode? Opening up, right? So mode 1. That's what we do in hydraulic fracturing. You're gonna see a picture on the next slide after this. And this is the conversation we've been having since the beginning of the class, that, yeah, we just say, as long as the pressure exceeds S3, you have a fracture. But really, you have to exceed not just the S3, you also have to exceed what? The tensile rock strength. And we had said the tensile rock strength is negligible, and that's what you're seeing here. So just to create the smallest fracture, you can require some considerable stress value, although this is not really big. This is just 300 psi, and you already know S3 in the formation deep down will be very large, right? It will be on the order of thousands of psi. So this is really negligible relative to the magnitude of S3. It comes out in the wash. So as you begin to extend the fracture length further and further, so the fracture is propagating as you move in this direction. It's in meters. You notice there is a sharp drop in pressure minus S3. What's this pressure? This fracture pressure. The pressure of the fluid in the fracture. This is the pressure of the fluid in the fracture minus the least principal stress. So it's showing you how far you need to exceed S3 before you propagate the fracture at different lengths of the fracture. So when you get to about 1 meter, you only need about 50 psi to keep the fracture propagating, which is why we say the tensile strength of the rock is immaterial. That value is the tensile strength of the rock at that length. So it's very negligible, regardless of whether the rock is very strong or weak. This is 50 psi, this is 25 psi. And you're looking at S3 value of, say, 10,000 psi. So this is really nothing. And that's the moral of the story. Once your fracture length exceeds about 1 meter, the strength of the material is irrelevant. The tensile strength is negligible compared to the magnitude of S3, compared to the magnitude of the pore pressure, the fracture pressure, which is the pressure of the fluid in the fracture. And that's when you're injecting fluids, right? You're doing hydraulic fracturing. So you'll be injecting fluid under pressure. You'll be using a compressor from the surface to push the fluid down. Any questions on that? 42, I have 8 minutes. So this is how your hydraulic fracture looks. Your well will be here in the middle. These are the normal compressive stresses in the earth, S3, as the least principal stress. Why do you think the fracture opens up against S3? Why can't it open up against S2 or S1? Thermodynamics. To minimize the energy expended in creating a fracture, it will open up against the least stress. So that's what's happening here. So it will always open up against the direction of the least stress. And this is your vertical well, right? You're looking at it from the top. And once you know the direction it opens up against, then you know the direction is going to propagate. It's going to propagate 90 degrees to that. So if this is the direction it's opening up against, yeah, then it's going to propagate here. So you know that this is the direction of SH max. And of course, this is the direction of SH min.
It's going to propagate to S2, correct?
S2, yes, we have assumed you're in a normal.
Okay. I just want to make sure.
Yes. So this would be S2 if you're in a normal faulting regime. So for it to open up against S3, it's going to be going in the direction of S2. And you can see that expressed in different ways. They say, yeah, your fracture propagates in the direction of the maximum horizontal stress. Same deal. It opens up against least principal stress. But that's really what drives it. It's trying to minimize the energy to create, or the work done to create the fracture. And this is actually work done, right? What is work? Force times distance. So the distance is that aperture, right? And the force is that force you need to overcome the SH mean. That's force per unit area. So everything still checks out with fundamental physics. And that's your fracture pressure, pressure of the fluid in the fracture, which has to overcome S3 before the fracture opens. And as the fracture opens, it tends to continue to propagate. And when this length becomes more than 1 meter, tensile strength is already negligible. And that's your mode 1 fracture. This is equation for stress intensity factor. I is the mode. So for mode 1, which is what we are looking at, this is K1. Fracture pressure minus least principal stress pi times square root of length. That's how it changes. So it's some measure of like the energy in the system, and that has to be greater than a critical or threshold value for the fracture to continue to propagate. That critical or threshold value is the critical intensity factor, which is also known as fracture toughness, the resistance of the fracture to propagate further. So you calculate this value, compare it to KIC, fracture toughness. If it exceeds KIC, the fracture continues to propagate further. And that's a field called linear elastic fracture mechanics when we model fracture propagation.
Does that SH max provide any resistance to the fracture propagation?
No.
At all, or is it just going in that direction?
No, it doesn't actually govern it in any way. What the resistance to it is the fracture toughness. Because the SH max is acting this way, right? But the fracture is opening up this way. And what keeps it going, regardless of what's in front, is that concept I had explained, that stresses concentrate at the fracture tip. So the magnitude of the stress at the fracture tip is the largest. It's greater than anywhere else in the domain. So it just passes through whatever is in its way. And the force that resists it is the fracture toughness. And that's what I was going to define here, is the amount of energy you need to propagate the fracture further into an unfractured material. So it indicates strength. And that's pretty much what I have on this slide. Any questions on this? Now I see some notes I had written before, which is important. Materials fail in compression when the compressive stress exceeds the compressive strength, right? And for tension, yeah, the tensile stress will exceed the tensile strength. And what's the tensile stress? Is that fracture pressure you're applying on it, right? When it exceeds the strength of the rock in tension mode, which is the tensile strength, then it opens up. And I only have 2 minutes. And I can start this slide, which I already discussed before, right? Very similar to the Moore column, but mu is not mu I. It's the coefficient, is the coefficient of frictional sliding on the surface. And you still continue to have these two normal, effective normal, and shear stress along the surface. Yeah, I need it was about to act up. Okay, I'm back. I'm on 4G, but I should be on 4. Good. And that's your column failure function. Column failure function. Actually, Coulomb failure function. And you can rearrange this, right? So this multiply both sides by effective normal stress. Then take all of them to one side. And that's your failure function. If this is equal to 0, then the rock mass will slide. And you can think about it as before it's equal, it's going to be less than, right? When there's no fracture. So that value will be negative before the fault block begins to slide. Then once it becomes equal to 0, then it slides. And again, reminder, that's your effective stress. It's the simple or Terzaghi effective stress. I explained previously this, right? More column was for an intact rock, meaning no pre-existing fractures. But here we're talking about cases where you have pre-existing fractures. CFF is always negative, like I showed. And when it's equal to 0, then the rock slides. And this is the important part. What happens to this when pore pressure is increased? So we can think about this, right? So tau, sigma is what? It's S minus pore pressure. So if you increase pore pressure, this goes down, right? If the denominator goes down, what happens to the ratio? It goes up. And it can eventually become equal to the mu, the coefficient of internal friction. And now the rock slides. And when the rock slides, what you have is seismicity, right? Earthquakes. So it can actually induce earthquakes. And it has actually induced earthquakes in real life. And this is for a case in Denver. This is for a case elsewhere. You're looking at the number of earthquakes expressed as frequency. You're looking at the amount of water they are injecting. So this is a water injection project, and actually waste injection project. This is the volume of the waste injection. You see, as you increase more volumes, well, you have more earthquakes. Increase more earthquakes. You don't inject within this time frame, well, little or no earthquakes. You begin injecting again, more earthquakes. There is the concept in statistics that correlation does not imply causality, right? So you're saying this is correlated with that, but actually here we know that's what's going on. The pore pressure is increasing and you're reducing the denominator, increasing. That's the entire ratio tau over sigma n, and eventually equals coefficient of internal friction, which is usually about 0.6. Same deal here. Lots of injection. Well, there was no data here. You reduce injection, fewer earthquakes, and that's what's going on. And I'll stop at that because we're past time. Any questions? So remember, this time next week, you'll be doing your midterm, and it's going to stop right here. Actually, we're going to make it stop at the end of that. So one more slide, which isn't really much of a big deal. So this is where we stop. There's still more on module 4, but that's where the quiz is going. The midterm will get to. So go through all the videos, see if you have any questions all the way from the beginning up to this point, and ask on Thursday. All right, any questions?
What kind of questions could we expect in the midterm? Like, will it be like similar to the way the quizzes are set up, or?
Yes, so most of the questions will be like the quiz, but I'm thinking I will have one question on calculation. And that question on calculation will require you to just enter the solution. Then on top of that, scan your solution. That way you can get partial credit. So you will put in the value in a box or in a line somewhere using model quiz functionality. Then it will give you an option to be able to upload, just the same way your assignments are, right? You will be able to upload your solution. That way you can get partial credit. But I'll give you more information on that as soon as I set the actual question. But there will be lots of the quiz kind of questions, right? OU, meaning multiple choice questions. All right, any other questions? Yeah. All right then, see you guys Thursday.